in time.
In time.
Okay, so last time we introduced chapter 4. So it's about the periodic table and some atomic properties. So before this chapter, we introduced how to fill the atoms or elements into the table, right? So and also we introduced how to calculate the energy of the electrons in the atoms. We also learned how to calculate the energy difference between the orbitals. Okay, so we will continue to study chapter 4. So here is the classification of the elements. So basically, for this is the electrons with outside electrons are filled in S and P orbitals. We call them representative elements. So these two parts are called representative elements. And the center elements are called D block elements. We also know in these elements there are two series of inner elements. One is about length lines, and this is about externite. Okay, so basically, in the same group, the elements have the same outside electron configuration. For example, for the group 1A, so the most outside electron is filled in NS orbital. So there, because it only has one element, so all these group have all elements in this group have the electric configuration like NS1, and in this group is NS2. Okay, and basically for the D block elements, so the outmost elements, electrons are filled in D orbitals. And for these elements, so there are outmost electrons are filled in like NP orbitals. So in this group, the electron configuration is NS2, NP1. This is NS2, NP2. And this is called a noble gas. So basically they are stable. They are electron configuration. It's like this, NS2, NP6. And it's also called full octet. So here is about the octet rule. Octet means the full energy levels are very low energy. If the atoms have low energy, so this means these atoms are stable. So we know noble gases have full orbitals, so they are stable. So for other elements, they tried to become the full energy levels, full orbitals. So this is called octet rule. So for example, we know for oxygen we know its electric configuration is 1s2, 2s2, 2p4. So basically, it tends to get another 2 electrons, and then to form 2s2, 2p6. So this is full full orbitals, so it is more stable, So basically, Austrian tend to get two electrons and to form two minus charge, okay? And the fluorine and it only need to get only one electron to form 2s2, 2p6. This is we know these elements are no metals. For metals, so basically they tend to lose the electrons to form the full orbital. For example, for sodium, so at the electron configuration is 2s2, 2p6, and 3s1. So basically, it is easy to lose this one electron and then form the full orbital electron configuration. So it tends to show a +1 charge. Okay. So this is about the octet rule. So octet rule basically is very common. It's commonly used for representative elements. And for D block metals, you also can use this rule. Okay. So basically, we know for sodium, for metals, they lose electrons to form ions. Okay, but for no metals, so they tend to get electrons, to form the electric atoms, ions. And for noble gases, basically they have full orbital electric configuration, so they are stable. They don't want to get or lose electrons. Okay. So here we can see for the representative elements for group 1, basically they usually show +1 charge. Okay, and for group 2A, so they show +2 charge. And for these no metals, they show the -1, -2, or -3 charge. But for this, so maybe they are more complicated because they can get 4 more electrons or lose these 4 electrons. Okay. So here, now we can see for some atoms, for some ions, they will show. So this is about the transition metals. So transition metals, they can show more charges, more kinds of charges. But for example, for iron, okay, it's basically for nicotine is formed from iron of a transition metal. Electrons are always removed first from the ns orbital, and then from the -1 d orbitals. For example, in this case, so iron it tends to lose these 2 electrons firstly, and then it can lose more electrons from D to form 3+ charge. Okay, and then we also introduce more properties about the elements later in this chapter. Okay, so here is about isoelectronic. So what is isoelectronic. So basically, they have the same number of electrons and hence the same ground state electron configuration. For example, for these ions, they have the same number of electrons, right? For oxygen, for example, oxygen, sodium lose, if it loses one electron, okay, it is like neon, okay, and this is lose 3, and they have all them have the electron configuration like 1s2, 2s2, 2p6, right? So when these two metal lose electrons, and for this non-metal get electrons, they will have the same number of electrons. So these areas are called isoelectronic. Okay. Okay. Now the question is, what neutral here is neutral? Okay. Neutral atom is isoelectronic with hydrogen. Hydrogen here is get hydrogen atom. Sometimes basically it lose one electron, but sometimes it also can get one electron. If it gets one electron, it will form hydrogen -1, right? So which neutral atom? Helium. Helium, yes. Why?
Because it contains one electron.
Yes. Yes. Because when hydrogen get one electron, it means it has 2 electrons, right? And then the helium, so it's like 1s2. 1s2 for the neutral is helium. Helium has the 1s2. So these two, they are isoelectronic. Okay. And of course, although they have the same number of electrons, they are not the same elements, right? Because they have different numbers of protons, right? Protons. Basically, the elements is decided by the number of protons. Each element has different number of protons. They may, for cations or ions, they may have the same number of electrons, but they are numbers of protons are different, so they are different elements. Okay. So in this table, periodic table, here we can like draw a line here. Okay. So this line is called zigzag line. So what this mean? So basically, this line can separate the elements to two parts, right? To the left, basically to the left of this line, they are metals. Okay. To the right of this line, basically they are non-metals. They are gases. But near elements along the border, along this, close this line, so they may have intermediate properties, and those elements are called metalloids. Okay, so like this kind of metalloids. Okay, so for this side is metals, and this side is no metals. Okay, so yeah, this is. I think this is easy to understand, and you know, for this are metals, these are gases. Okay, so here like this. Okay, so all these are metals, and these no metals. But these elements are called metalloids. Okay. So this is about the zigzag line. So it can separate the elements to metals and non-metals. So basically, for metals, they have some common properties and common properties. For basically, for the metals, right? So metals basically they are good conductors. They can transfer electrons. Okay, and but for no metals, so basically, no metals are gases, and they are poor conductors. They can't transfer electrons. For metals, we know the electrons can move between the atoms, so they can transfer electron. And for metalloids, so basically they are thin conductors. So they basically used in the computer chips. Of course, the metals and the non-metal have much more properties. Here, we just show some common and simple properties. Okay, so for atom, so this slide show the atomic radius. We know for metals, basically they are structured like this. Okay, so if this is one atom, so each atom they just stay together, right, like this. So in this structure we can define the metallic radius. So metallic radius is the distance between these two centers, right, and half of the distance between these two centers. So this is metallic radius. But we know for no metals, their structure is not like this. Not like this. Okay. For example, for some gases, so they are a compound. They're compound. Compound, compounds mean they have one more elements. So for example, in this case, these two atoms can be same. So anyone can give us example for this gas. No. Carbon dioxide means 3 atoms.
Oxygen gas.
Carbon oxide, no.
Oxygen gas. Oxygen gas.
Yes, oxygen. Because CO, they are different atoms. So the size should be different. But here, they size the same, right? So we can oxygen gases, okay. So in this case, so we can only find the covalent radius. Covalent because they are covalent bond. So we can get the covalent. So this radius is different from this mechanical radius. Okay, this is about atomic radius. So here is show the if it is a single atom. So this is the atomic radius in the table, in the periodic table. So from here we can say, so this is one series, right? So from left to right, the radius increase or decrease. From this, you can see the size. So the size is the radius, means the radius. So from left to right, there are radius increase or decrease. Decrease. Yes. See, this is bigger than this one, right? And more small and small. Okay. This is so you should remember in one series. This is a series, right? One series. So each series like this also the same, right? So from the right to left, the radius decrease. Okay. And in one group, from this one to this one. So increase or decrease?
Increase.
Yes, increase. You can see this is much bigger than this one, right? And this also, this group also the same. So here, yeah, we can see from left to right, decrease. From up to down, increase. Increase. So we often are using this figure to show the tense in atomic radii. So this is one group, okay? This is, we know this is 1A group, right? 1A group. This, okay? This is 1A group, 2A group, okay? So in one group, from up to down, it increase. This is one series. This is one series. So from left to right, distance. So in one period, this is one period, okay? So this is one period. So the atomic radii is like this. Okay. So this is neutral element. The atomic radii means that they are neutral when they are neutral, okay? But we know the elements may get or lose electrons, right, to form more stable ions, more stable ions. Okay. So basically, for metals, we know when they lose, they tend to lose electrons to form plus charge. After they lose electrons, they are reduced. We can say increase or decrease. Decrease. Yeah. See this one. Okay. This is for metals. For no metals, we know the tends to get electrons to form stable four orbitals. Four orbitals. Okay. So when they get electrons, we can say they are reduced, increase or decrease? Increase. See, this floral, right? The radius is this, but when we get it's big. So here, from here, we can see the metal, the cations, basically the cations is small than their atom, than their neutral atom. Okay. For an irons, they are larger than they are neutral element, neutral atom. Okay. So now so it's like this. So lithium, okay, is the size. This is the size of lithium. Okay, this size of fluorine. The first lithium is much bigger than fluorine, right? But when they form this compound, so this lose one electron, so the size is small, right? And the fluorine, when it change to an iron, it's much bigger. It's like this. So cation is always smaller than atom from which it's formed, and an ion is always larger than their atom, than their neutral atom. Okay. Yeah. This here we can see very clearly the changes of their radius. Okay. So here we can see the ions, the radius of the ions. For example, for these cations, their size like this. Okay. And for an ions, the size like this. So from here we can see the ions basically larger than the cations, right? The cations. And basically, if they are neutral, for example, if they are neutral, so this one is large or this one is large. You remember? In a period from left to right, they are for neutral atom. They are reduced, increase or decrease. In a period from left to right.
Decrease.
Yes, decrease. So decrease basically means this is smaller than this one, right? But now we can say when they form iron rings, so this is much larger than this one, much larger than this one. Yeah, question? Yeah.
So what's the reason behind the increase in radius when gaining electron?
Why? Right. Good question. So we will explain later. Okay. Now. Okay. So this picture shows the irons, the radius of irons. Okay. So now we should explain why, for example, in one period from left to right, y decrease, right? And in one group from up to down increase, right? And also we didn't know why the cations is small than their neutral atom, right? And also an irons always larger than their neutral atom. Yeah, for these 4 questions, now we explain why. So basically, here to show the attraction and the repulsion of the charges, of the electric charges. So, for example, between these 2 atoms, when they have different charge, so for example, one is plus charge, another is minus charge. So basically, if they have different charges, they will attract each other, right? Okay. And if they have same charges, they will repel each other. Okay, if we separate, so like this, right? And also they will separate each other. Okay, so now we know, yeah, they will attract each other. So this is about the attraction and the repulsion forces between the atoms, between the ions, Okay. Now we can see the structure of the atom, For example, for this metal, they have the nucleus is plus charge, right? They have protons. Protons have plus charge, okay? And the electrons, they have some electrons outside, right? So basically, the electrons, we can separate these electrons to 2 parts. One is called inner or kernel electrons, or inner electrons. Another part is just the most outside layer. So this is called valence electrons. For example, we know for this metal, its electron configuration is 1s2, 2s2, 2p6, and then 3s2. So this called inner electrons. Okay, this one is most outside, right? The third layer, first, second layer are called inner electrons. So this is called valence electrons. Valence electrons also means basically, for example, they're easy to lose this, right? These elements for metal, and if there are no metal, so basically in here they usually get electrons, right? So basically here we call them valence electron orbital. Okay, valence electron orbital. Okay, now we know between the nucleus and the electrons, they attract each other, right? Because they have difference. But between the electron, like inner electron and the valence electron, they will attract and repel. Yes, they will repel each other. So, for example, for inner electrons, they are just attracted by the nucleus, right? But for the valence electrons, besides the attraction right? They also, yeah, get the repulsion force from the inner electrons, right? Because the electrons they repel each other, right? So they also get some repulsion forces from the inner electrons. So what this means? This means for this more close to the nuclear, right? But for this, they also attracted by the nuclear, but they also are repelled by the inner electrons. So they can't, so it looks like they can't get as much forces from the nucleus as inner ones, right? So this is called shielding effect. Shielding effect to the valence electrons. Okay? So this means this electron, this inner electron can shield the nuclear forces to the valence electrons. Okay? So here we introduce what is shielding effect. So any question for the shielding effect? Shielding effect means for the inner electron, they can only attract by the nucleus. But for the valence electrons, they also be repelled by the inner electrons. So this means they looks like they lose some attraction from the nucleus. So this is about the shielding effect of the inner electrons to the valence electrons. Okay? Yeah.
At what number of electronic shields does the out electrons start to repel? Since
Yeah, they will repel each other.
yeah, like at what number of what's the electronic shells? Like since the first shell, second shell, third shell. I mean, when do they start repelling? When do they start bouncing off the other shells? Since like they're, for instance, those are two electronic shells. That one's like going to.
So basically, we just separate the all electrons to two parts. All this is called inner. All this is called valence. So just the inner, and of course 1s, 2s, 2p, all these 10 electrons will repel this. Okay. Now we just consider the valence. The valence is just put two parts, and of course they also repel each other. But we don't discuss the repulsion between this. We just discuss put them two parts. This part and this part, and of course this part can repel this part, right? Okay.
Wait.
Yeah.
So the valence electron, you just get the last one.
Yeah. Oh no. All this, because they have the same orbiter, right? They have the same layer.
I mean, just the last.
Yes, last layer. Last
So
layer
only
of
one
orbiter.
last layer, only one last layer.
No, two, both, two. Because these two electrons are same, right? They are same, they are at the one orbiter, right? In one orbiter, so they are same. So both of them are repelled by these electrons. Yeah. So we just consider this layer of orbiter. Okay. Okay. So here we can say like this. So this is inner electrons, right? These two are valence electrons. So this one attracted by this, okay? And of course they also attract by this, but they also repel each other, right? So this can repel this electron. So okay. So here we can using this when we know the Sheldon effect, so we can use this Sheldon effect to explain why in table, in the periodic table, from left to right, the radius decrease. For example, these three elements are in one period, right? It's the second period, right? Or the second period. So, for example, this has three electrons. This has four. This has five electrons. So here, as the attraction between the nucleus and the valence electrons increase, if they actually increase, so the atomic size will decrease, right? This means because the valence, if the attraction between the nucleus and the valence electrons increase, so this means the valence electrons are attracted much more by the nucleus, and of course, it will tend to close to the nucleus, right? So the radius will decrease, right? Okay, so from left to right, size decrease because there is an increase in nuclear charge and effective nuclear charge. So here, effective nuclear charge. So what is effective nuclear charge? So effective nuclear charge means proton number minus the core or like inner core electrons. So this number is called effective nuclear charge of the valence electrons. Okay, here we just give an example.现在上课你丢在旁边就可以了，然后我们下次开始来。So for example, this is, so for this, so how many protons? Three, yes. It has 3 protons, right?
Yeah.
So 1s2, 2s1. So how many inner electrons? 2. Okay. So 1 is valence, right? So in this case, what is the E and C number? How much? 1. Yes. Because using 3 minus 2, right? So equal 1. Okay, then I should break.